Welcome to G Fun Facts Online, your go-to spot for mind-bending science. Today, we're diving headfirst into one of the biggest mysteries in physics. Is gravity quantum? For decades, this question has stumped the brightest minds. We have two rockstar theories explaining our universe: Einstein's general relativity for the big stuff, like planets and galaxies, and quantum mechanics for the tiny, bizarre world of atoms and particles. The problem? They just don't play nice together, especially when it comes to gravity. But what if we could finally peek behind the curtain? Stick around, because a groundbreaking experiment at MIT is using a literally chilling technique that might just give us the first clues. So why is this such a big deal? Imagine having two instruction manuals for reality. One describes a smooth, flowing universe where gravity bends space and time. That's general relativity. The other describes a universe built from tiny, discrete packets of energy, full of probabilities and weird connections like entanglement. That's quantum mechanics. We've managed to fit all the other fundamental forces, electromagnetism, the weak and strong nuclear forces, into this quantum rulebook. But gravity? Gravity's the stubborn kid in class, refusing to join the quantum party. Trying to quantize gravity leads to mathematical nightmares and, more importantly, we've had no experiments to guide us. Until, perhaps, now. Okay, so gravity is a bit of a loner in the quantum world. Why should we lose sleep over it? Because cracking this nut could unlock answers to the universe's deepest secrets. A quantum theory of gravity could explain what happened at the very instant of the Big Bang, when our current theories just throw up their hands and say, infinity. It could tell us what's truly going on at the heart of black holes, those mysterious cosmic vacuum cleaners. Is space-time smooth? Or is it a jittery quantum foam at the tiniest scales? Why is gravity so ridiculously weak compared to other forces? And the ultimate dream for many physicists: a theory of everything, a single, elegant equation describing all forces and particles. The payoff is huge. This brings us to the cutting edge, to an incredible experiment unfolding at MIT. Researchers there, led by PhD candidate Dong-Chel Shin, are trying something audacious. They're taking a classic tool for gravity research, a centimeter-sized twisting device called a torsional oscillator. Think of a tiny, high-tech seesaw that twists, and giving it a quantum makeover. The chilling part isn't just a pun. They've cooled this oscillator from room temperature down to an astonishing 10 millikelvins. That's just 1/100th of a degree above absolute zero, the coldest anything can possibly be. This is the first time anyone has laser-cooled a torsional oscillator this big. How do they do it? They shine a laser onto a tiny mirror on the oscillator. Any tiny twist makes the reflected laser beam shift, which they can measure with incredible precision. They even developed a way to cancel out laser jitter noise by a factor of 1,000, allowing them to detect motion almost 10 times smaller than the oscillator's own inherent quantum jiggle. The goal is to get this normally classical macroscopic object so cold and so quiet that its quantum nature, its inherent quantum fuzziness, becomes observable. They want to see how gravity interacts with an object that's both big enough to feel gravity strongly and quantum enough to show its quantum side. Cooling it to 10 millikelvins is a massive step, but the team wants to go even further, to reach its quantum ground state, where its motion is purely quantum. And here's the really mind-blowing part, the ultimate dream for this setup. Imagine two of these ultra-cold, quantum oscillators placed near each other, shielded from everything else. If these two oscillators become quantumly entangled, meaning their fates become linked in a spooky quantum way solely because of the gravitational pull between them, that would be it. That would be direct experimental proof that gravity itself is a quantum phenomenon. It would strongly suggest the existence of the graviton, the hypothetical particle that carries the gravitational force. Goosebumps, right? The stakes for an experiment like this are astronomical. If they observe these quantum gravitational effects, say gravity-induced entanglement, it's Nobel Prize territory, folks. It would confirm gravity is quantum and give us the first real experimental data to guide theories like string theory or loop quantum gravity. It would mean gravity can carry quantum information. But what if they find nothing? A null result wouldn't necessarily mean gravity isn't quantum. The effects might just be too tiny for even these incredible instruments. But it would still be super informative. It might suggest gravity is fundamentally classical, or that its quantum side only shows up at energy levels we can't reach yet. It would force physicists to rethink their entire approach. Now, MIT isn't alone in this quest. This experiment is part of a whole new wave of tabletop quantum gravity experiments. Scientists are a clever bunch. Other teams are trying to levitate tiny diamonds and put them in two places at once to see how gravity affects them. Others are using the wave nature of atoms in atom interferometers to measure gravity with mind-boggling precision. There is even an experiment called G-Quest at Fermilab in Caltech using super-sensitive laser interferometers. And, of course, theorists are constantly cooking up new ideas and connections, some even using quantum computers to simulate bits of quantum gravity. For so long, testing quantum gravity seemed like science fiction, something only possible by looking at the entire universe or smashing particles at unimaginable energies. But thanks to incredible advances in controlling quantum systems, precision measurement, and cooling things down to almost impossible temperatures, we're entering a new era. The challenges are still immense. Gravity is incredibly weak at these scales, and isolating its quantum signature is like trying to hear a whisper in a hurricane. But the potential reward, understanding the very fabric of reality, is worth every bit of effort. These chilling experiments are not just cool tech. They're paving the way to answer one of the deepest questions we've ever asked. The next few years could be revolutionary. So, will gravity finally join the quantum club? Experiments like the one at MIT are bringing us closer than ever to finding out. What a time to be curious about the universe. That's all for this episode of G Fun Facts Online. We hope we've tickled your quantum brain cells today. Join us next time for more fascinating facts from the world of science. Don't forget to subscribe and stay curious.